Hello everyone, my name is Shouqiao Wang, and today I'm very excited to present our recent work, Optimal Dynamic Fees for Blockchain Resources. This is a joint work with Davide Crapis, who's from Ethereum Foundation, and Professor Ciamac Moallemi from Columbia Business School. There will be 4 parts for this talk. First, I will introduce the transaction fee mechanism and show what questions we are facing. The second part, I will talk about the model and corresponding optimal policy. Then we will dive into some empirical results based on our model. And the last part is for the summary and future extensions. First of all, blockchain needs a mechanism for pricing congestion. So Bitcoin is using auctions. Ethereum uses dynamic posted price, which is the base fee mechanism in EIP 1559. The EIP 1559 takes the gas used in the previous block, which is YK in this equation, as an input to determine the base fee of the current block. So when the demand is above the target, it can increase the base fee by up to 12.5% to reduce the demand, and vice versa. So EIP 4844 marks a significant evolution in fee markets by introducing data gas as a second resource. Note that blob transaction will consume both gas and data gas, and the gas fee and data gas fee are updated independently. Today, the resources such as compute, bandwidth, storage, they're all bundled together, which we call gas. In the future, we may see different kinds of resources being created. A very natural way to create new resources is that we can unbundle gas and rebundle them into new resources. So the main reason that we want multiple resources for designing a fee market is to allocate the network congestion more efficiently. So in this paper, we want to answer the question of how we can design the multi-dimensional transaction fee mechanism. Then how should we design? So ideally, the fee mechanism needs to be simple, robust, and optimal. So simplicity means it should be straightforward to implement and easy to understand. Robustness guarantees our system should be built with withstand unpredictable market changes and protect against manipulation. And optimality shows that our mechanism needs to be the most efficient under some criteria. The contribution of this work is that we propose a new multidimensional transaction fee framework, which is adept at managing an arbitrary number of resources, ensuring a balanced approach to the deviation of resource use from target and price fluctuations. And also it is optimal under our settings. So there are several ways to use our framework. First, it can be directly implemented for most L2s and for some nimble L1s. Alternatively, our framework would offer some insights to refine existing heuristics for Ethereum Layer 1. Lastly, we provide some valuable guidance on defining the multi-dimensional resources, which can be priced independently and effectively. Then I would like to talk about the literature review on blockchain transaction fee mechanisms. So Vitalik Buterin's initial work laid the groundwork by proposing a dynamic base fee system, leading to extensive research and development within the Ethereum ecosystem. Later, Tim Roughgarden published a paper on game theoretic analysis of EIP 1559, and Riceburton et al. Did some empirical studies. The field further evolved with Buterin's introduction of multi-dimensional transaction fees, aiming for enhanced scalability and efficiency. Then, David Crapis did simulations and analyzed EIP4844 policy. Recent studies such as those by Diamandis et al., Leonardo et al., and Ferrara et al. Delve into designing optimal fee update rules, addressing both static and dynamic aspects of pricing in multidimensional settings. And here comes our model. So first, we can define an n-dimensional vector T as the target of our multi-dimensional resources. So at every block K, what the protocol can observe is only the base fee Pk and the realized demand in the previous block Yk. Both of them are n-dimensional vectors. So we use a linear demand model to model the realized demand Yk. You can see in the middle of this page is Yk equals to dk plus bk times pk plus epsilon k. But the parameters like the potential demand dk and price sensitivity bk, they're not observable in the protocol. So in practice, we need to estimate the parameter dk and bk in order to calculate the optimal policy. And here is an example of the two-dimensional independent resources. So you can see the decreasing linear function in these two graphs are the demand curve of these two resources respectively. T1 and T2 are their corresponding targets. And this is the case when the cross price sensitivity parameter beta 1, 2 and also beta 2, 1 are both 0. However, in our model, we can allow the cross-price sensitivity parameter with respect to any two different resources to be non-zero. For example, in our framework, we can let beta 1, 2 and beta 2, 1 to be non-zero. And here is our objective function. So our objective function, as you can see, it has two parts. The first part is the square of yk minus t. This refers to deviation of realized resource demand from the target t. And the second part, the square of pk minus 1, refers to the price fluctuation. And lambda is about how we balance these two costs. The price for block k plus 1 only depend on the historical data available up to block K. And so under this setting, this optimization problem will fall into the category of linear quadratic Gaussian control problem, which is a celebrated dynamic programming problem, which guarantees the existence of explicit solution. So after solving this optimization problem, our optimal fee, pk plus 1, is a weighted average to the previous price pk and a parameter called mk. The parameter mk is a weighted average of all of the future market clearing price, ps bar. The first part of the weighted average, which is pk, this part is for reducing the price fluctuation. And the next part, the mk, is for reducing the resource demand deviation. And there's also a parameter called qk over lambda. It can optimally handle the trade-off between these two targets. And this result is analogous to Gardiano and Patterson 2013, where he considers the linear quadratic Gaussian problem in a different setting. So these slides, we compare our optimal policy to the EIP 1559 policy. In EIP 1559, the fee is updated based on the previous block gas used yk. However, in our policy, we're not directly using yk. we're using the prediction of the gas used for the current block k plus 1 in this equation, which is the conditional expectation of yk plus 1 conditioning on all the history ik. Moreover, EIP1559 uses a fixed coefficient 1 over 8, but we are using the price elasticity of the demand at the target, which is eta k in our formula. So we also compare our policy versus the EIP 4844. So similar as previous slide, we are using the estimated resource demands, which is the conditional expectation of yk plus 1, rather than the demand from the previous block to update our fees. And moreover, for EIP 4844, the price of each resource updates only based on the demand of this resource itself, which means P1 only depends on Y1 and P2 only depends on Y2. But there may exist some cross-sensitivity between these two resources. For our policy, we can jointly update our price based on the expected demands. And here's a question. So why is it necessary to jointly update the fees? This is essentially because in EIP 4844, the price of gas or data gas individually will affect the demand of both gas and data gas. For example, if the gas fee skyrockets, then there will be nearly no demand for both gas and data gas. No matter how much is your data gas fee, there will be nearly no demand because the blob transaction will also consume the gas fee. So that's why the jointly update is really important. And in this paper, we also argue a simpler way to price the transaction fees. Under the eigenresource framework, we can separate the n-dimensional joint pricing issues into n one-dimensional pricing issues. Essentially, our approach does not address these n resources directly. Instead, we focus on specific linear combinations of these resources, which we call eigenresources. The eigenresources do not have any cross-price sensitivity. Just you can have a look at the last equation. The price sensitivity matrix for the eigenresources yk tilde is a diagonal matrix of delta k. So since there is no cross-price sensitivity, we can price the fee for each eigenresource individually. For more details, you can read the eigenresources section in our paper. As you can see, the design simplifies the complex multi-dimensional pricing problem into several one-dimensional pricing problems, which will enhance the efficiency of the protocol. Thus, it will provide some insights for the practical resource design. Next, let's look at the empirical analysis of our framework. So we use a 14-day period one-dimensional Ethereum layer 1's data and observe the total gas used yk and base fee pk for each block. They are all one dimension. We estimate the parameters in our model by a commonly used algorithm called EM algorithm. And here's the graph that we estimated the potential demand dk and the price sensitivity beta k. We observed that these two parameters change over time in practice, so we cannot assume they are constant. We additionally use two mean reverting process to model these two parameters as shown in the equation of this page. Observe that the price sensitivity parameter beta k is stochastic, as we just demonstrated in the previous slide. This optimization problem will no longer fall into the linear quadratic framework, which means we are unable to get the optimal policy explicitly. While we can't achieve an explicit optimal policy due to the stochastic property of beta, we've adapted by developing a heuristic inspired by model predictive control. In this approach, we continuously update our estimation of futures beta, leveraging all available historical data. We then calculate the optimal policy based on the assumption that the futures beta will align with these estimations. Although it is not optimal when beta varies stochastically, our empirical results suggest that this method serves as an effective and implementable heuristic, aligning closely with real-world application needs. Using this heuristic, we compare our optimal policy versus the EIP 1559 policy. Just recall that lambda is the parameter for balancing the cost between the deviation of realized demand to the target T and the price fluctuation. For example, if lambda equals to 0, it means we only care about the cost of the deviation of realized demand to the target. If lambda equals to infinity, it means we only care about the price fluctuation. In this table, we will mainly focus on RMSD and RMSU, which represents the cost of the deviation of realized demand to the target and the price fluctuation, respectively. If we choose lambda to be 10 to the power of -7, our policy can improve RMSD by 6.0% and RMSU for 21.4%. Note that even when lambda is 0, we can only improve RMSD by 6.0%, which means EIP 1559 does a really good job on handling the deviation of the demand YK to the target T. However, it has room for improvement on decreasing the price fluctuation, since the RMSU of our policy is significantly better than the RMSU for EIP 1559. And this graph shows the difference between our optimal policy and EIP 1559 during a demand spike and demand uptrend. When there is a demand spike, our policy can adjust the price quicker and greater in order to better decrease the demand to the target. When the demand varies gentler, our optimal price becomes smoother than the EIP 1559 policy. Here are two histograms of the gas cost and transaction price. It shows that our policy reduces extreme deviations on gas cost and smoothers price change on average. Note that our policy hits the gas cap 2T less frequently as shown in the left graph, meaning that it does a better job on DSIC, which is the dominant strategy incentive compatible. And now we will summarize our work and discuss some future extensions. So in this paper, we propose a general framework to model multidimensional resource pricing and calculate the corresponding optimal policy. It can be directly implemented for most layer 2s and some nimble layer 1s. It will also offer some insights to refine existing heuristics for Ethereum layer 1. While our findings indicate challenges in minimizing the deviation between realized demand and the target, there appears to be a viable pathway to mitigating price fluctuation. Inspired by the structure of our optimal policy, it may be possible to propose a new mechanism that could be both robust and implementable within Ethereum Layer 1, especially designed to smooth out price fluctuations. We also provide some insights on the multidimensional resources design problem. And here are several open problems. First, after the launch of EIP4844, we can do some empirical analysis of our bidimensional fee policy. Additionally, there are challenges of defining practical resources for multidimensional pricing on Layer 1, ensuring efficiency and fairness. Lastly, we explore the framework variations for optimal pricing of some Layer 2 resources in the future. And here's the reference. And that's all of my presentation. Thank you for listening.